So, in order to understand what enzyme kinetics is and what Km and Vmax means in relation to enzyme kinetics, we need to understand what the Michaelis-Menten equation and graph look like first. So this is the Michaelis-Menten equation. And Michaelis-Menten equation basically shows us how the velocity of an enzyme, of an enzymatic reaction, increases with an increase in substrate concentration until eventually the graph reaches a plateau because the enzyme is fully saturated with substrates. And this is the Michaelis-Menten graph for question 1 of our lab. So as you can see, the velocity of the enzymatic reaction increases and then eventually it plateaus. When the graph reaches its plateau, that means that the enzyme is fully saturated with substrates and it cannot possibly convert substrates to products any faster than it already is. The next equation we need to talk about is the Lineweaver-Burke plot, which is essentially the reciprocal version of the Michaelis-Menten equation. This is the Lineweaver-Burke plot of question 1 from our lab. And as you can see, it is a straight line instead of the Michaelis-Menten graph. And you can even see the equation y equals 3.11x plus 0.664. So essentially, y equals mx plus b. With this graph, we're able to calculate the Km value and the Vmax value of an enzymatic reaction because the y-intercept is equal to 1 over Vmax and the x-intercept is equal to negative 1 over Km. And this is just explaining how exactly I found those values. So we already know that y equals 0.664 because of the equation on the graph. So you do 1 divided by 0.664, and that's how you get the value for Vmax. And then for Km, you just solve for x, and then you do negative 1 divided by negative 0.2135, and then you get 4.683. So for question 2, we were asked to do the same thing, except this time we were comparing graphs between enzymatic reactions on their own and then an enzymatic reaction with 2 inhibitors. So this is the enzymatic reaction on its own with no inhibitor. As you can see, this is the Michaelis-Menten graph, and it increases and then eventually plateaus. And by the way, Vmax would be somewhere above somewhere along the lines of 0.8 on the y-axis. This is the Lineweaver-Burke plot of question 2, the enzymatic reaction without an inhibitor. And as you can see where the line of best fit crosses the y-axis and where it crosses the x-axis. And this is how I was able to figure out what Vmax and Km were for this reaction. So this is what the Michaelis-Menten graph looks like with inhibitor 1, and I can tell just by looking at it that Vmax may have increased. This is the Lineweaver-Burke plot and the equation for inhibitor 1. So Km for the reaction without the inhibitor was 1.136, so that didn't really change that much or at all. And then Vmax for the reaction without the inhibitor was 1.125. So Vmax for inhibitor 1 increased. Since Vmax actually increased, I actually don't think that this is an inhibitor. This looks more like an activator because activators increase Vmax while inhibitors usually decrease Vmax. This is the Michaelis-Menten graph for inhibitor 2, and I can tell that Vmax, it looks like it decreased. This is the Lineweaver-Burke plot for inhibitor 2. And these are the calculations for inhibitor 2. So Km and Vmax were both decreased when compared to the enzyme without the inhibitor, which tells me that this is uncompetitive inhibitors. Uncompetitive inhibitors bind to the enzyme substrate complex. This action causes the enzyme's active site to become distorted, which inactivates the enzyme. Therefore, Km and Vmax are decreased.